All right, guys, we're going to talk about analysis of variance, which is also called Anova for short. Okay, so what we've been looking at before, we've been looking at z-scores and t-scores, okay? When we want to compare the means of two different groups, right, we don't want to make multiple t-ratios, okay? That increases the odds of making an error. So instead what we do is we do an Anova, an analysis of variance. That's one overall decision as to whether or not there's a significant difference. Okay, so what happens when we need to make comparisons between more than two groups, right? We can't use the t-test. If we do that, it increases the type 1 error. If you remember, type 1 error is when we reject the null hypothesis and we say there's a real actual difference, but there isn't one. Okay, so analysis of variance in Anova holds those type 1 errors at a constant. So to conduct Anova, we're treating the total variation in a set of scores as being divided into two components, okay? How much difference there is within the groups, okay? That's the distance of those raw scores from their group mean, and how much variation or difference there is between groups, so from one mean to the other. Okay, so that's kind of our three parts there. So what Anova gives us is what's called an F ratio. Okay, the numerator, the number on top, is the between groups, and the denominator is the within group. Okay, so that's telling us how much difference there is between groups relative to the difference within their own groups. The larger the F ratio, the greater the probability of rejecting the null hypothesis, okay, and showing that indeed there is a real significant difference between the groups. Okay, and here we've got comparison across four groups: lower class, working class, middle class, and upper class. So notice on the top, we've got the between group variations, okay, the differences between the X bars, and on the bottom, the variation within the groups. Okay, so the first concept we need to learn about in order to do this is called the sum of squares. Okay, and this refers to the sum of squared deviations from the mean. Okay, so remember, this kind of backwards looking E means sum. X is our score minus X bar of the total, right? The average of the total group squared. So this is similar to some concepts we've looked at before. Okay, then we're going to look at between group sum of squares and within group sum of squares. So let's take an example. Suppose a criminologist wants to look at the extent to which race and ethnicity of a violent juvenile offender influences whether or not the public supports trying that offender as an adult. Okay? So it creates four versions of a hypothetical case of an armed robbery committed by a 15-year-old male. The only difference is he's changing the race and the ethnicity of the perpetrator. Right? He randomly assigns 20 subjects to one of the four condition groups. So our null hypothesis is public support for trying an offender as an adult does not differ by race. Our research hypothesis then is that public support for trying the offender as an adult does differ by race. So does the race of the juvenile make us change our mind about whether or not we should try them as an adult? Okay, so the total sum of squares is defined as the sum of the squared deviation of every raw score from the total mean. The within group sum of squares is the sum of the squared deviations of every raw score from its group mean, and the between group sum of squares represents the sum of squared deviations of every group mean from the total mean. Okay, so here's how we would compute this, right? So we've got when the juvenile is white, when the juvenile is black, when the juvenile is Latino, and when we don't tell you what the juvenile's race or ethnicity is. So let's just look at one of these. So let's look at the one for white, okay? X1 is all of our scores, right? That's the scores for group 1. 1, 4, 2, 6, 2. Okay? So then X minus X bar, so X minus the average, and then X minus X bar squared. This is similar. We've done this in a couple other places before, right? And we're going to sum those all up. And we're going to do that for each scenario. Okay. So using that formula, you can see here that we're going to subtract the total mean from each raw score, square the deviations, and then add them. So that's kind of the thing we just looked at, right? Here it's done out for us. And done out for us again and again. So take a minute to look at these PowerPoints and read through them, because we're just kind of skipping through them. Okay, so here's our computations then. Right, here's that math done out for us. Okay, the next concept we want to understand is the mean square. Okay, so the value of the sum of squares grows as the variation in sample size increase. So the mean square or variance controls for those influences, right? So we want to control for that change. So we've got MS between, MS within. Remember we also talked before about degrees of freedom, and here K means the number of groups and N is still our sample size. All right, so now let's calculate an actual F ratio. So once you've computed the F ratio, then we have to look at it to see if it's significant. So the F ratio is the MS between over MS within. Okay, the larger it is, the more likely it is to be statistically significant. And we're going to use Table D in Appendix C. Now, if you ever find yourself unable to find these or you don't have access to the PDFs that are on Blackboard, you can just Google F ratio table and you'll be able to find it on the internet. When we use Table D, we need to look then for 2 degree of freedom values, the between group degree of freedom and the within group degrees of freedom, okay? So let's look at how we do this. Okay, so here we've got our data. We've got 3 samples, sample A, sample B, sample C. Then we've got our analysis of variance summary table, right? Then we've got another one, right? So we've got an F ratio of 48 in the first one and an F ratio of 3.2 in the second one. So let's walk through an example, okay? So our null hypothesis is that students in urban, suburban, and rural high schools do not differ in terms of how safe they feel. Our research hypothesis then is that we think that it does differ, students in urban, suburban, or rural high schools, okay? So here we go. We've got 5 random students from urban, suburban, and rural high schools, and we give them a fear of school crime inventory, okay? It ranges from 0 for fearless to 10 for extremely fearful, okay? And here we've got our data below. So we've got the data, the actual scores, if you look under the first one for urban schools, X1, and then X1 squared. Okay, and we've got that for each group of students. Okay, so the first thing we want to do is find the mean for each sample. We know how to do this. This is just finding an average. Okay. Then we need to get the sum of scores, sum of squared scores, number of subjects, and mean for all groups. Okay? We're going to use those then to find the total sum of squares. So we're just going through step by step, plugging things into our equations. Then we're going to use that information to calculate within group sum of squares and between group sum of squares. We want to get our degrees of freedom, and then we want to find our within groups mean square. Our between groups mean square, and then we're finally down to we have our F ratio of 8.24, okay? So now we want to look that up. Our ratio is 8.24, and in table F, we have degrees of freedom 2 and 12, and we're trying to look at this at a significance level of 0.05. So the table F ratio there is 3.88. So we have exceeded that, okay? So just like with our T-scores, we're looking for a critical value. We need to exceed 3.88, the value in the table, in order to reject our null hypothesis. So there is an actual difference. High school students in urban, suburban, and rural locations do differ in terms of their level of fear. Okay, so now we want to talk about conducting a multiple comparison of means to determine where a significant difference lies. So the F ratio tells us there's a difference between those 3 groups, but it doesn't tell us where, okay? So we can use Tukey's HSD to determine this. It allows us to compare any 2 means against this HSD, okay? So we find this Q is found in table E, root of MS within divided by N group. So let's look at an example of this, okay? We get this fearlessness of high school students, right? We find that this is different based on whether or not a student's in an urban, suburban, or rural location. But how do we know which one matters? So we have our X bar for each group. So for group 1, it's 6.2. For group 3, it's 3.8. And for group 3, it's 3.2. So we want to now construct a table of differences between ordered means. Okay? So look at our first row, right? We're not going to compare 3.2 to 3.2 because that's the same mean. But the difference between the average for group 3 and group 2 is 0.6, and the difference between group 3 and group 1 is 3.0. And then we just need to do between group 2 and group 1 for 2.4. Okay, so in order to get Q from table E, we have to have the degrees of freedom for MS within, the number of group means K, and a significance level either 0.1 or 0.05. Okay, we already know that our degrees of freedom within is 12. So we're going to go down that left-hand column of table E until we arrive at 12 degrees of freedom. Okay? We're comparing 3 mean scores, so we're going to go over to a group means of equal to 3. So Q is 3.77. Okay, so we're going to find the little bit more than cubed, 3.77 of the square root, 3.77 times the square root of 1.5 over 3. Right? So that's 3.77 times 0.553, which means 2.08. Okay? So now, any obtained difference between means has to exceed 2.08. Okay? So, we know that when we go back to that table of differences of means, right? Step 1 here. Does anything exceed 2.08? Right? So the difference between x3 and x1 and x2 and x1 does meet that requirement. Okay? So the difference, the only place it isn't significant is between rural and urban schools. So just remember, with any of these tests, we need to meet certain requirements. So we're comparing 3 or more independent means. We need interval level data. It needs to be a random sample that's normally distributed, and we're assuming that there's equal variance. And we literally just did the same slide. So my apologies for having it in here twice. And that wraps up Anova.